To define a finite set of numbers, we usually rely on explicit enumeration. We simply write out every single item, enclosing the list inside curly braces. But this method mechanically fails the moment we encounter infinite data. If we try to explicitly enumerate the set of all integers, the stream of numbers never stops. We quickly run out of space. It is mathematically impossible to list continuous domains, like the real numbers, where there are infinite values between 0 and 1 alone. Because we cannot list infinity, we have to change our approach. We have to construct sets using strict algorithmic rules. In mathematics, this rule-based construction is called set comprehension. Set comprehension serves as the architecture for continuous mathematics and computational data pipelines. Instead of trying to list infinite data, we build pipelines to query it. On the left is the mathematical syntax for set comprehension. It looks like static notation, but it actually reads from left to right as a three-stage mechanical flowchart. On the right, we see how this breaks down into a generator, a filter, and a transformation. Stage 1 is the generator. You cannot create a set out of thin air. You have to define an existing domain to extract elements from. Here, we are pulling the variable n from the natural numbers. This generator acts as the raw material intake for our algorithmic pipeline, supplying a continuous stream of inputs. Stage 2 is the filter. We apply a Boolean condition to call the raw data stream. In this case, we check if n is less than 500. This gate ensures only data meeting our logical constraints moves forward. The rest is discarded. Stage 3 is the transformation. Surviving elements are mathematically mapped to their final state. Here, each number is cubed before being deposited into the new collection. Manually calculating and listing 500 cubed numbers is inefficient. This single expression executes the exact same outcome instantly. The system is entirely modular. You can change the filter to only allow even numbers, or change the transformation to calculate squares instead of cubes, without altering the raw input data. This exact structure is mirrored in computer science. What mathematicians call set comprehension is identical to functional programming pipelines using map, filter, and reduce operations. We can apply this exact architecture to more complex domains, like the rational numbers. A rational number is just a numerator and a denominator. We can use set comprehension to filter out equivalent fractions, like 2/4 and 4/8, keeping only the reduced fractions. We achieve this by applying a specific constraint. We only let the fraction pass the filter if the greatest common divisor of the numerator and denominator equals exactly 1. This logic also scales to the continuous gapless space of real numbers. Here is a number line representing the space between 0 and 1. Set comprehension allows us to define precise geometric intervals. The syntax uses the inclusive inequality. 0 is less than or equal to r, which is less than or equal to 1. We call this a closed interval. The less than or equal to notation dictates that the interval explicitly includes its exact endpoints. If we exclude those endpoints, we get an open interval. The boundary limits are strictly applied, replacing the inclusive symbols with strict inequalities. Because this is an algorithmic pipeline, we can mix these constraints. We can create left open or right closed intervals simply by adjusting the logic for each endpoint independently. Set comprehension provides the geometric boundaries necessary to navigate, constrain, and manipulate continuous mathematical spaces. Once we construct these sets, we need a way to combine and query them. We use operations like union, intersection, and difference to map propositional logic directly onto geometric space. A union combines sets X and Y. The entire footprint illuminates, but center elements are deduplicated and counted once. This center slice is the intersection, containing data surviving both conditions. Isolating X and excluding Y yields the set difference, illuminating only the left crescent. Unlike basic arithmetic addition, set difference is strictly non-commutative. Subtracting Y from X yields this left crescent. Subtracting X from Y yields a different geometric space on the right side. The final major operation is the complement, which seeks to define everything that is not inside a specific set. But the complement has a negative constraint. You cannot compute a complement without first explicitly defining an overarching container, known as the universe. If your universe is the set of natural numbers, taking the complement of prime numbers yields the composite numbers. But if your universe is the real numbers, the complement of the crimes includes fractions, pi, and irrational decimals. Defining the universal boundary is a mandatory first step. Without a defined overarching container to govern it, the spatial logic collapses. We can apply this spatial logic to solve problems in overlapping datasets. Consider a university class with 50 total students. 30 take physics, 25 take biology, and 5 take neither. This creates a numerical discrepancy. If we add the physics students, biology students, and the students taking neither, the sum is 60. We cannot have 60 individuals inside a 50-person universe. To solve this, we measure cardinality. Denoted by vertical bars, cardinality is the strict numerical count of elements contained within a set's geometric boundaries. First, we isolate the active universe. Subtracting the 5 inactive students leaves 45 taking at least one subject. But our two active sets, 30 and 25, add up to 55. This exceeds 45 by 10, proving 10 students sit in the intersection, being double counted. With the intersection mapped, we can query specific data, like finding students taking only physics. Applying set difference, we subtract the 10 intersection students from the 30 total physics students. This leaves a verified 20 in the isolated physics crescent. This spatial deduction allows us to programmatically reverse engineer missing variables and clean overlapping datasets. Set theory provides the computable architecture required to master infinite data. Through comprehension pipelines and geometric operations, it transforms mathematical categorization into an active processing system.